Now let's put it all together about what is the main memory, logical address and physical page size. Let's put everything together now. Okay. Assume that capital M is instead of saying capital M, let us say physical address space is equal to main memory size, isn't it? I'll not say this again and again, but it is the last time. Physical address size is equal to main memory size, and let us say it is M words. So capital M words represent the physical address space, which is equal to the main memory. And now logical address space is equal to process size, right? Process size, let us say this is equal to capital L words, right? And let us say page size is equal to P words. Fine. If this is the case, right, if this is scenario, then how many words, what will be the size of the physical address? See, physical address size means the size of the total memory, and physical address means number of bits which are used to access the physical memory. Both are different, right? And physical address will be log M base 2 seal. Actually we need not put seal, right? But then the reason why we need not put this seal is always capital M will be a power of 2, and whenever I take any logarithm for any power of 2 with base 2, I'll not get any fractions, right? I'll get a whole number. But then why am I putting this seal is, it is just for the conventional sake. Nowhere you are going to see that main memory is 100 bytes. No one is going to say that. It will be either 128 or 256 or something like this. Okay. Anyway, let's go with the conventions. Got it? And let me write it as small m bits. So small m bits are required for physical address, and logical address is nothing but number of bits required to address the process, which will be log L base 2 seal, and let me write it as small l bits. Okay. And now page size. So if page size is going to be P words, then how many bits are required in order to identify a word within a page? Are you following it? If page size is P words, then how many bits are required to identify a word within the page? That is what I am asking here. Then I'll call it as page offset. Page offset is nothing but if I want to identify a word within a page, then how many bits are required. So page offset can be obtained by putting log P base 2 seal. Let me call it as P bits, right? So if you want to know what all these bits mean, let's take a small example and I'll tell you this. Let us say physical address space equal to 128 MB, right? And logical address space equal to 1 MB, and page size equal to 4 KB, right? So what do you understand? Total main memory I have is 128 MB, and the size of each process is going to be 1 MB, and page size is going to be 4 MB, right? So if this is the scenario, then let's analyze all these numbers. Now in order to identify, okay, here whenever they say that the memory or everything is in bytes, and if they don't mention anything about words, think that each word is 1 byte. Got it? Sometimes they will not talk anything about the words, right? In case if they give you about the words, like each word is 4 bytes or something, convert everything to words and then solve the question. If they don't mention anything about the words, best thing is to assume that a word is equal to 1 byte, right? So you can leave it just like this in terms of bytes, and you can compute it, or you can replace bytes with words because nothing is given, and you can go ahead with the question. Now if this is the scenario, then what is the physical address? So if you have to identify all this, convert them into powers of 2's. What is 128? 2 power 7. What is M? 2 power 20. Therefore this entirely is going to be 2 power 27 bytes. And what about 1 MB? 2 power 20 bytes. And what is 4 KB? 4 is 2 power 2, K is 2 power 10. Therefore it is going to be 2 power 12 bytes, isn't it? Then if this is the case, if I have 2 power 27 bytes, in order to identify each byte within a within the physical address space, how many bits are required? Let's say logical address space is this. Let's say the process size is bigger, or okay, let's leave it this way, no problem. Physical address space, right? Okay. See, I want to extend this question a bit further. So if I take other representation, it will be better. Let us say logical address space is this and physical address space is this. If you observe this, logical address space means size of the process is 128 MB. Physical address space means the main memory available is just 1 MB. So if you observe this question, the process size is very much bigger than the main memory, right? Then what is this? Then the concept of virtual memory has to be used. Then logical address can also be called as virtual address. But anyway, people are using both the names simultaneously, which means sometimes they say virtual address, sometimes they say logical address. So don't get confused in that. Okay. Fine. Now, if the logical address space is 2 power 27 bytes, then how many bits are required in order to identify a byte within this logical addresses? So logical address is going to be 27 bits, isn't it? Then what about physical address? How many bits are required to identify a byte within 2 power 20 bytes? 20 bits, right? With 20 bits I can get 2 power 20 addresses, and each address can be associated with 1 byte. Got it? And what about this page offset? If page size is 2 power 12 bytes, which means in one page, if we have 2 power 12 bytes, if I have to identify one among these 2 power 12 bytes, then how many bits are required? 12 bits. Got it? Fine. So let's leave it here and let's extend this. Now we know that in this case, we know that physical address is m bits, isn't it? So why physical address is m bits? Because size of the physical address space, this entire size is actually 2 power m bytes, right? Or 2 power m words. So don't get confused. Words are the ones which we are worried about, and even if the question is given in bytes, we are going to convert it into words. So if the total physical address is 2 power m words, right, and then the physical address is going to be small m bits, right? And now you could divide, actually it is divided into various frames, right, in such a way that frame size is equal to page size is equal to p words, isn't it? So page size equal to frame size equal to p words, which means each page size here, this one, or each frame in this case is going to be p words, right? Then how many pages are there and how many words are present in each page? Now what I will do is 2 power m words are there, and each page is going to contain p words, right? So let me write this p in terms of something which I could divide. Okay, p bits here I have, right? So page size is going to be, or frame size is going to be 2 power p bits, right? And total physical address is going to be, physical address space is actually 2 power small m words. I think this is also 2 power m words, right? So are you following this? Each frame is 2 power p bits, and small p is nothing but I have derived small p from this, from page size only, right? Frame size is going to be 2 power p words, and physical address space is going to be 2 power m words, right? Then my question is, how many frames are present in this entire physical address space? So if you want to find the number of frames, right, then you divide the physical address space by the number of frames. So what is physical address space? 2 power m divided by what is the frame size? 2 power p. Then how many frames will be present? 2 power m minus p. Got it? So it is actually divided into 2 power m minus p frames in such a way that each frame is 2 power p, right? This is the division. Are you understanding this? The entire physical address space is divided in such a way that each the total total memory is divided into 2 power m minus p pages or frames, and each frame size is 2 power p words, right? So dividing it like this is meaningful in such a way that the most significant m minus p bits will identify what is the frame, and the least significant p bits is going to identify the page frame offset. Therefore, if you have to reach any byte within one page, what you should do is using this frame number. This is what I call it as frame number, right? And this is what I call as frame offset. So first, using this number, go into the frame, that particular frame, and then using this number, go into that particular word. Getting this, right? So that is how you can divide it. So now physical address is divided into frame number and then frame offset. Understood this? Similarly, you can divide the logical address space also. If you watch it, what is the logical address space? Logical address space is capital L words and which requires small l bits. Therefore, I can write the logical address as 2 power L words, isn't it? And what is the page size? Page size is 2 power P words, isn't it? What does it mean? Your process whose size is 2 power L bits, L words, is divided into many pages in such a way that each page size is 2 power P words. Now, can you tell me how many pages are present? Then the number of pages will be logical address divided by word size. Then how much is this? 2 power L divided by 2 power P, which is nothing but 2 power L minus P. Now you can write this entire address space as 2 power L minus P pages are present in such a way that each page size is 2 power P. Therefore, this is the total number of words possible. Are you understanding this one? Okay, then how can you divide the address? If you think that each address is going to contain L bits, right? If address is going to contain L bits, now that L bits can be divided into two parts. One part will contain L minus P most significant bits, which will give us the page number. This one I call it as page number, and least significant P bits is nothing but the page offset. Got it? So in order to get into a word in a process, first you go into that particular page, and after you get into the page, you use the page offset and go into that particular word, right? So that is how you are going to divide the main memory address, this physical address and logical address. I think you got how to divide the addresses, right? So let me just extend this concept. Hope that you have taken down this. Now you understood one thing. Even though I have m bits in the physical address space, it is going to be divided into two parts. One is frame number and other is frame offset. And even though we have L bits in the logical address space, it is also divided into two parts. One is page number and the page offset, like this. Physical address, which is equal to m bits in total. In total it is equal to m bits is divided into two parts. One part is frame number, right, and the other part is frame offset. So I think you understood now. Frame number is used to go into particular frame in the main memory, and then frame offset is going to go into the frame into that particular word. Got it? And now how many bits are here? So the number of bits required here will be m minus p, and the number of bits required will be p bits. Got it? And similarly, logical address space is going to contain two parts, right? So even though it is going to contain logical address is going to be split up like this. So logical address, which is equal to L bits, logical address is equal to L bits, and it contains two parts. One part is page number and other part is page offset, right? And how much is page number? Now page number will be equal to L minus P bits, and it is going to be P. Now if you observe it, either frame offset or page offset is always going to be same. Why? Because either it is a frame or a page, both sizes are same, right? And therefore the number of bits required to identify a word within a page or frame are going to be equal, isn't it? Therefore these two are going to be equal. Now the entire part of memory manager here, or memory management unit, is how are you going to take the most significant M minus P bits and convert it into L minus P bits. This is the entire part, right? Now how is that done is, we are going to use something called as page table. Page table. Page table. How does this page table operate is, see, now you found out that your logical address space or your process is divided into 2 power L minus P pages. See, if these many bits are there in the page number, then how many pages will be present? 2 power L minus P pages, isn't it? So now your page table is going to contain, the total number of pages will be 2 power L minus P pages, right? So for every page present in the process, there will be an entry in the page table. Okay, so try to understand this. For every page present in the process, there will be an entry in the page table. I already told you with an example, right? Therefore number of entries in the page table, number of entries in the page table will be equal to number of pages in the process, right? So if you have more number of pages in the process, then the number of entries in the page table will be more, isn't it? So what you could understand here is, therefore the total number of entries present in this page table will be equal to number of pages. And how many pages are there? 2 power L minus P. We just calculated it, right? Therefore the number of entries in the page table is going to be 2 power L minus P. And now assume that each entry size, which means this part, if each entry size is E bytes, then what will be page table size? Page table size, the size of the page table, which is very important because it is going to affect many things. I'll show you what it is going to affect later, but anyway you have to calculate the page table size. Now page table size is going to be, how many pages are there, which means how many entries are there? 2 power L minus P entries are there, and each entry is of size how much? E bytes. Therefore this is the total size of the page table. The total size of the page table is going to be number of entries multiplied with number of bytes for each entry. Now in the question, if they give you this page table entry size, then it is fine. If they don't mention anything about the page table entry size, then what you should be doing is this thing. Understand this? Sometimes they are going to say that page table entry size is some bytes. That is fine. But sometimes they are not going to say what the page table entry size is. Then what you should do is, you are supposed to calculate it. How can you calculate it is, watch it. What will be present in the page table entry? The page table entry will contain the frame number in which this particular page is going to be present. See, for example, page table entry will be like this. Page table entry will contain 0, 1, 2, 3, 4, 5. So these numbers which will not be present inside the page table, because it is just like an array, these are the indices of the page table, and each index represents the page number. So it represents that page number 0 is present in so and so frame, page number 1 is present in so and so frame, page number 2 of this process is present in so and so frame, right? And now therefore each entry of the page table actually contains the frame number in which that particular page is present, right? So for example, if this page table, if this page of the process is present in frame number 10, then it is going to contain page number 0 is going to be present in the frame number 10. Why do you need it? Because not to convert the logical address into physical address, we have to take the page number and go to that particular page and then take the frame number and put it there. Then we are going to, using this address we can go to the memory and get the word. And these bits they don't vary, right? Okay, now if they don't give you anything about this, then you can understand that the main entry that has to be present inside this entry is, in the page table is the frame number. Then how many bits are required in the page to represent a frame number? If you watch it, the number of bits required to represent the frame number is m minus p, right? So in case if e is not given, then page table size will be number of entries is nothing but 2 power l minus p, which is equal to the number of pages into the actual information that is present inside each cell of the page table is the frame number, right? And how many bits are required to represent the frame number? M minus p. Got it? So if they don't say anything about the entry size, right, then you can take this as the page table size. But the problem is, this is not actually true. In a sense, in most practical cases, we don't just save the frame number inside the page table. Along with the frame number in which the page is present, we save even more information about the page itself, like whether the page is modified or not, whether the page is referenced or not, or what is the history of the page, everything. We can save even the permissions like read, write, execute, everything we can save it, right? So what I mean to say is, in case if they don't mention anything about the page table entry, you go with this number, right? And this is going to give you the page table size. If they mention it, you go with this, right? In any way, at practice, your page table entry size will be much bigger than this one, right? Maybe we shall take this the same example, and then I'll show you how this entire thing works, right? And then we shall see lots of examples on this. We shall practice it until you cannot get it wrong. Okay. Now let's try to use this numerical and then find out what is the process that page table size and page table entry size, everything. So watch it now. So here logical address is given as how many bits? Logical address is nothing but 27 bits, and physical address is given as 20 bits, and page offset is given as 12 bits, right? Then how many pages will be there? We have to find out the number of pages, right? So in order to find out the number of pages, find out the number of bits. Okay, like this. Logical address is 27 bits, right? Now it can be divided into two parts. One part will contain page offset. So page offset is nothing but 12 bits, isn't it? And other part will contain page number. This is page offset, and other part will contain page number. Now if the total size is 27 and if I remove 12 bits, how many bits will be remaining? 15. Therefore page number will contain 15 bits and page offset will contain 12 bits. And now physical address space. Physical address space will also be divided into two parts. One is frame offset and other is frame number, right? So frame offset is going to be 12 bits and frame number is going to be 8 bits, right? And therefore the number of pages possible is 2 power 15. The reason is the page size is page number field is containing 15 bits. So number of pages possible equal to 2 power 15 pages, right? And what about page size, page table size? Now the page table should contain one entry for each page, right? Now how many pages are there in the process? 2 power 15 pages are there in the process. Therefore the number of entries in the page table will be 2 power 15, right? And what will be the size of each page table entry? That depends on the implementation. If they don't mention you anything, then a page table entry will contain the frame number, right? And what will be the frame number here? Frame number is nothing but 8 bits. Therefore each page table entry contains 8 bits, which is 1 byte, right? So the total page table size will be equal to 2 power 15 is number of entries into size of each entry is 8 bits, right? This is the total page table size in bits. Now what will be this in bytes? 2 power 15 into 1 byte, isn't it? 8 bits is nothing but 1 byte into 1 byte. Therefore it is 2 power 15 bytes. Got it? So in this numerical, the page table size is 2 power 15 bytes. Now watch it. The page size is how much? Okay, well, how much is 2 power 15 bytes? If you see this, it is 32 KB, right? So page table size is 32 KB, but the page size is, where is it? Yeah, but the page size is 4 KB. Now watch it. So page size is 4 KB, right, and the page table size is 32 KB. What does it mean? The page table itself is so big that it cannot fit in one page. Then what should be done? Again, this page table has to be divided into many pages, right? That is called as multi-level paging. We shall look at it later. First we shall practice all these questions a lot, and then we shall go into the multi-level paging. So I think you got the concept, right? Now the process is very big, so I have divided the process into many pages, and then I have kept it in various frames, and now I got the page table. Now the page table is also big in such a way that it cannot fit in one frame. Then what is that we are supposed to do? Again, divide the page table also into various pages, so that the page table will fit in many frames, right? Then in order to get the a page, first you go to the page table and then get the page table entry, and then go to the page and then get the required word. Therefore there has to be multi-level paging. Okay, anyway we shall see it later. Fine, so let's go step by step. Right now if I tell you what is multi-level paging, you will not understand anything. So let me make all these points clear in a simple manner, and let us practice lots of questions on this, then I'll move ahead. Okay, so if you are very perfect about all this, then you can skip the next video which will contain examples about these concepts. Okay, fine.